Alright, so this is a probability review. We are going to review the main probability rules. And so I'm just going to give a quick review of what all of our probability rules are, and then we'll see it in examples. So, probability rules. Rule 1. If you're given all outcomes, the probabilities should add to 1. Assuming there's no overlap. And 1 being 100%. Alright? Probability should never be over 100%. The max you can have is 100, and you can never have a negative probability. Okay, so your probability of some event A, this is our notation, probability of A, is going to be between 1 and 0. Okay, rule 2, the complement rule. That is the not rule, not it kind of rule. So it's saying the probability of not being A is everything 1 minus A. That's the complement rule. So let's say you had 30% are girls. The probability of not being a girl is 1 minus 30% or 70%. We'll see an example of that later. The OR rule. When you see OR, it is the addition rule. OR means add in probability. So if you see P of A or B, and you can write OR with that big U. Okay, P of A or B, that's the probability of A plus the probability of B. And if there is some overlap between A and B, you need to make sure you're not double counting anything. So you take out the probability of both. And those are the double counted people. Okay, now that's the addition rule. And now we're going to do the multiplication rule. So this is when you have multiple events, or we might call it compound events. This is our multiplication rule. And this is when we did dashes, if you remember that. That's like saying P of A and B. And you can write like this. We didn't do that very often, but for college, A and B is the probability of A times the probability of B. Okay. All right. So these are some of our big rules. There's a couple more. We also had the at least one rule. And that was like saying everything except none of them. So the probability of at least one A out of 5 different objects is everything except no A's, or none of A. All right, and the last one is the conditional probability. And that is the probability of something given another thing. So it's given a condition. So it's like the probability of A given B, and oftentimes we'll write it as A given B. So knowing that B is true, what's the probability of also A? So that is the same as saying, okay, given B, that's our denominator. We know we're only looking at the B's. What's the probability of also A? So we would put A and B on the top because we know B has to be true. What's the probability of also A? Okay, so you could write it as P of both over the given. Okay, So these are all of our probability rules that we've worked with in chapters 14 and 15. And then chapter 17 is binomial, which I should give you another video for that. So let's do some examples for this review. So I'm going to come up with a scenario. Let's say we're looking at starbursts. All right, so we're going to look at starbursts that have the following. So let's say we're looking at like thousands of starbursts. And so all the possible starbursts coming out of the manufacturing plant, starbursts have the following distribution. Color distribution. Okay, when we say distribution, we just mean like how are the colors distributed. So orange, this is not true, but we're just gonna go with this. Orange is 0.21, or 21% are orange, so this is like the possible outcome, and this is the probability of that outcome. All right, so orange is 0.21. You could have red starbursts, and like let's say 26% are red. You could have pink starbursts, and let's say 28% are pink, and the rest are yellow. So if you pull just one starburst out, what is the probability it is yellow? Starburst. What is the probability of yellow? Well, how are we going to find this missing thing? We know that these are all the possible outcomes for starbursts. You can only have orange, red, pink, or yellow. There's no other option. And all of these should add up to 100%. So right now they don't. What is this? 60 plus 15. This is 75%. So that doesn't add up to 100%. So the rest of it, everything except that 75, should be the yellows. So the yellow is 25%, which means I can put that 0.25 into my table. Okay, so that's the everything should add up to 100% rule. Now let's try the complement rule. If you pull one starburst, what is the probability it is not orange? Well, orange is 0.21, which means not orange is everything except orange. So it's 1 minus orange, or 0.79. Okay, so you can try the complement rule now. How about you try? Pause the video and try this, the probability of not red. Your turn. Try it right now. Pause the video and try it. Okay, so the answer is everything except red, or 0.74. Okay, so that's the complement rule. Now let's keep going and try the addition rule. So let's say I want to pull out a starburst. What is the probability it is red or pink? Well, we know that or means add because our probability should be increasing. So I know the probability of red. I'm just going to rewrite my table over here. So I know that the probability of red is 0.26 and the probability of pink is 0.28. So it should be the probability of red plus, or means add, the probability of pink minus any overlap they have, minus both. Now, is there any way for you to have both a red and a pink starburst when you just pull out one? No, there's no such thing as a swirled starburst yet, though there should be. So for now, this is 0. So the probability of red is 0.26. The probability of pink is 0.28. And there's no probability of both. You can't have both a red and a pink. So we just take that minus 0 and we get 54. Okay, what we call this is if you can't have a both, if there's no both, we call this disjoint or mutually exclusive, meaning they share nothing in common. So they share no events in common. There's no probability of both. You can't have both. All right, that's disjoint or mutually exclusive. You usually represent this like this, or you could represent it with this, but this is empty. Okay, there's no both. They're completely separate events. They're mutually exclusive. All right, so let's think about, okay, let's consider a scenario where it's non-disjoint, where it's not mutually exclusive, and see what that looks like. So let's consider another scenario, because starbursts are disjoint events, starburst colors. So let's think of a scenario where it is non-disjoint scenario, not mutually exclusive scenario. Let's just stick to the candy theme, and let's think about Hershey's Kisses, or like the little chocolates. So let's say we have a giant jar of Hershey's. So we have thousands of Hershey's. In a jar. And I tell you that 80% of this jar is milk chocolate. Okay, 35% is white chocolate. And 25% is both. Okay, those ones are actually my favorite. Those are the hugs, you know, where they look like this and then they have like that swirl. So good. Okay, gotta make the tag on top. All right, so these are like the hugs. They're the swirled ones. So they're both milk and white chocolate. Now let's say I ask, what is the probability of milk chocolate when you pull out a Hershey's Kiss, milk chocolate or white chocolate? Well, if I pull one out, I want milk or white chocolate. You would think, okay, I'm just gonna add these. But notice that when you add them, it goes over 100%. That's because 25% is in here, and it's double counted in here, right? Like if I pull out a hug, I'm gonna record it as milk chocolate and white chocolate because it has both. So with that in mind, we need to be like, okay, I want milk chocolate plus the probability of white chocolate, but there are some double counted, so I need to take out that double counted group. So that would be 0.80 plus 0.35 minus 0.25. So 90% are milk chocolate or white chocolate. So then I might ask myself, well, what's the probability of being not milk nor white chocolate? So I pull one out and it doesn't have either milk or white chocolate. Well, I know that the or is 0.90, so that's like, if I'm gonna visualize this, I know that this whole circle here is milk, and I know that consists of 80%. And this circle here is white, and that whole circle is 35%, and in the middle is 0.25. Okay, and so I know that these circles together make 90% because milk chocolate or white chocolate, that's these circles together, is 90%. neither, not being milk nor chocolate, is on the outside. So if this whole thing, when I add it up, is 0.90, neither is going to be everything else. So 1 minus 0.90. Okay, and so we used to do these Venn diagrams. We could also find the probability of milk chocolate with no white chocolate. Like my mom, she hates white chocolate. So she doesn't like Hugs. She wants just the milk chocolate ones. And so that would be the 80% that are milk chocolate, but take away the Hugs. And so that's this bit right here. Take away this 0.25 and you get 0.55. So this is 0.55. This bit is what she likes. She likes the shaded region, so she doesn't like this thing in the middle. All right, and that's how we used to do Venn diagrams, so hopefully you remember that stuff. Okay, so that's the OR rule looking at addition. We've got a few more to go. We're halfway through. So we've got the multiplication rule, the at least one rule, and conditional probability. So let's go back to our starburst. So here's our starburst. And we're gonna look at the multiplication rule. All right, so let's go back to starburst. So I guess I'll just draw a line here and we'll look at this multiplication rule. And the multiplication rule occurs when you have more than one event. So it's called compound events. I'm just gonna skip that up a bit here. So the multiplication rule would be, so the multiplication rule goes when you have multiple events. So let's say we're dealing with the starbursts again, and we're pulling multiple starbursts. So let's say if you pull 3 starbursts, what's the probability they are all pink? And this is when we did the dashes, if you remember the dashes. So it's like 3 starbursts and they're all pink. Okay, so pink is 0.28 according to up here. So these are all 0.28. And it should be much harder to get 3 pinks in a row than just 1 pink in general. So it should be harder, and so then that means our probability should be decreasing, which means we multiply. And this is why it's the multiplication rule. Another way that we can write this is 0.28 to the 3rd power. And that gives us 0.022. Okay, so instead of a 28% chance of pulling a pink, which is if you pull out 1 starburst, that's the chance you get pink. To get 3 pinks in a row, it goes all the way down to 2% chance. All right, and so this is how we use dashes. We could do, if you pull 3, what's the probability all 3 are pink or red? You can pause the video and try that on your own. Again, it's 3 dashes, and they're all pink or red. So we know that pink or red from earlier up here is 0.54. So they're all 0.54. And so that's 0.54 to the 3rd. Or 0.157. Okay, and so this is the multiplication rule. There's many different applications. We'll do a couple more practices. Okay, and I'm still sticking with the original orange, red, pink, yellow, orange is 0.21, there's my cat, red is 0.26, pink 0.28, and yellow is 0.25. And so let's say what is the probability that if you pull, sorry, let me just move her a sec. So let's say if you pull 4 starbursts, what is the probability the last is the only yellow. Well, you have 1, 2, 3, 4. This one's yellow. And the rest here are all not yellow, because this was the only yellow, so these had to be not yellow. We know that yellow is 0.25, and using the complement rule, we could understand that not yellow is everything except 25, so that's 75. And we multiply all of these together. Okay, and this leads us to the at least one rule. Let's say we wanted to know what is the probability of at least one yellow out of 4. For some reason we want yellow, I don't know. So we want at least one yellow. That means what we want is 1 or more yellows. We're like, I want 1 yellow or 2 yellows or 3 yellows or 4 yellows. These are all things I want. And I don't care if it's the first one is yellow or the last one is yellow, as long as at least one is yellow. That's what I want. So there's like a ton of different ways that we can make this happen. And so that would be a lot of probabilities to figure out. But the only thing we don't want is no yellow. And that's only one probability that we have to figure out. So we'll find the one thing that we don't want to happen, no yellows at all, and we'll say I want everything. I'll take anything other than no yellows. So if all of them not yellows. And so that's the at least one rule. So that's probably one of the harder ones because it's hard to kind of wrap your head around taking away the one thing you don't want. Okay, so that's the at least one rule. So this is a good review. Now there's one more thing that we might want to consider. Oh, I guess there's a couple more things. One more is the conditional probability. So normally we see conditional probability. You've seen it before, and you probably would know this just by looking at it, but you see it normally you see it when you're given a table. So something like this. Let's say this is like men, women, and we're looking at long hair and short hair. I don't know, we can just make stuff up. Okay, so you see a table like this and we're talking about hair. All right, and so you might see a table like this. Conditional probability would be like, what is the probability given a person has short hair, they are a man? This is conditional probability. We have a condition that we know is true. We know that they're given short hair. So this is what we put on the right side, short hair, and we want to know what's the probability they are a man. Okay, so what we do is we're looking only at the short-haired people, looking at short-haired people out of those 30 people. So that becomes our denominator. What's the probability they are also a man? Well, that's that top number, 20. Okay, so this is really our given is our denominator. And so it's given they have short hair. What's the probability they are also a man? So what's the probability of having both short hair and being a man? Okay, and so that's like this. Okay, so you've seen that before. It may not be as obvious. It may not say given in the problem. You might see something like, what is the probability of a woman having short hair? The given here is that it's a woman. What is the probability of a woman? There's no doubt that this is a woman. We want to know what's the probability she has short hair. So now it's kind of flipped. Given woman, what's the probability of short hair? So our denominator is looking at all the women. What's the probability of short hair? All right, so this is conditional probability, and you can see it not just in a table format, you can see it with anything really. So you can see it with, let's say we were looking at the starburst, and we're like, what is the probability, knowing you got at least one yellow lemon. They are actually all yellow. So we know we had at least one that was yellow. What's the probability it was actually all of them being yellow? So that's given at least one. What's the probability of all yellow? Well, we know our denominator is that at least one yellow, what we calculated before, and our numerator would be all of them yellow, which is 0.75 times 0.75, 4 times. Okay, so that's 0.463. All right, you can also see it in a long word problem format. So let's say there is a 30% chance that it rains on Monday. If it rains on Monday, there is an 80% chance the bus runs late. If it doesn't rain, buses sometimes kind of stink. There's still a 30% chance it's late. Knowing the bus, or given that the bus is late, what's the probability it was raining? Okay, so in this case, it's like really hard to digest. So the way that we do this, when we see a bunch of like ifs, when one depends on the other, we're probably gonna be making a tree here. And so I don't know if you remember trees, but this is what trees look like. It's either raining or not raining on Monday. It says there's a 30% chance it rains, which means there's a 70% chance it doesn't rain. If it rains on Monday, there's an 80% chance the bus is late, which means there's a 0.20% or 0.20 chance or 20% chance it's not late. Okay, if it doesn't rain, there's a 30% chance it's late, which means 70 that it's not late. And to finish our tree, we multiply across. And so this is our tree, and we use this to answer the question. Knowing that the bus is late, so given that it's late, what's the probability it was raining, also raining? So our denominator is late, which is here and here. And our numerator is where it was also raining. It's the both late and raining. So raining and late. So this is a 53% chance. All right, and so those are trees. And so this is everything that we did in probability. Now there is one thing that you need to consider with probability, and that is the population size. So in all of these examples that we've been doing, we've had either no population given because we've had just like looking at starburst just in general. And here in our chocolate example, we had thousands of Hershey's in a jar. It would change if we had a small population. So in all of these circumstances, we had large populations or unknown populations. But if you have a small population, that you choose your sample from, especially like compared to your sample. Then the probability of each event may change. So let me show you what I mean by that. Let's say we only had 20 starbursts. And what we're going to see is that we need to use fractions. So let's say we only had 20 starbursts. Okay, 5 are yellow, 6 are pink, 2 are orange, and 7 are red. Right, that makes 20. 11 plus 9 is 20. Okay, so let's say we pick, if I pick 3 starbursts. Sorry, that's my dog. He thinks it's dinner time. He has another hour. Schmitty, shh. What's the probability they are all yellow? Okay, so if I'm picking 3, I want them all to be yellow. I think about pulling the first one and I'm like, okay, well 5 out of the 20 are yellow. So there's a 5 out of 20 chance I pull that yellow. And then I eat that starburst, there's no longer 20 there. And there's no longer 5 yellows. There's only 4 yellows and there are 19 starbursts. And then the next time there's only 3 yellows and there are 18 starbursts. And notice that 5 out of 20, this is 0.25, but 3 out of 18 is 0.16. So there was actually a significant change in probability because you had such a small population size. If your population size was like 10,000, 5 out of 10,000 is 0.0005, and 4 out of 9,999 is 0.0004. So there's like hardly any difference. There's a 1,000th difference, whereas here there's a 9% difference. Okay, so because it changes the probability so much when you have a small population size, you use fractions to calculate that probability, and you would actually just multiply it as you see it. So 5 out of 20 times 4 out of 19 times 3 out of 18. Okay. Oops. Okay, so this is what it is when you calculate it correctly. If you had actually done 0.25 times 0.25 times 0.25, you would get a much larger percent chance, a much larger probability, when truly it's actually a smaller probability. So you need to use those fractions when you have a small population size. And typically we consider a small population size one in which the sample is greater than 10% of the population. That's when you have if your population is small, then your sample, this 3, is greater than 10% of 20. That's true. 3 is greater than 2. So my population was so small that I needed to use fractions. Okay. So you can do that with anything. You could do what is the probability? The first is the only pink. So you've got these 3 dashes. This first one is pink, and there's a 6 out of 20 chance it's pink. And then these ones are not pink because the first one is the only pink. So there are 9 plus 5 is 14 that are not pink, but I already took one of them out, so there's actually 19 left, and then I want another not pink one. And then I would multiply as I see it. All right, and so this is all of our probability rules all up in one, and there will be a practice for you to practice this work, but this is everything you need.